Hello, in this video we are talking about section 7.2 on volumes. This is our second day of lecturing on section 7.2, so we're focusing on volumes by washers. Now this is really just an extension of the disk method, because with the disk method we end up with cross-sectional areas that are disks or circles. So we have one radius that we need to find. With the washer method, we end up with cross-sectional areas that have that look like a washer. So we have an outer radius and an inner radius that we need to find. Now in example 3, we have a region bounded by the curve x equals tangent of y, the line y equals 1, and the line y equals 0. This is revolved around the y-axis to generate a solid, and we are asked to find the volume of the solid. So the steps that we're going to work through here are very similar to what we had with the disk method, and so we're going to start off by sketching the region. Now let's start with the curve x equals tangent of y. If we solve for y, we get y equals the inverse tangent of x. So then the question is, what does the inverse tangent function look like? Well, if you don't know what it looks like off the top of your head, the easiest way to graph it is to instead graph the tangent function and then to flip it over the line y equals x, because these are inverse functions and that's how graphs of inverse functions are related. So for the tangent function, we have vertical asymptotes at negative pi over 2 and positive pi over 2, and the tangent function looks something like this in between. So then if we graph y equals inverse tangent of x, we're going to have horizontal asymptotes at pi over 2 and negative pi over 2. And if we draw the line y equals x and then flip our curve over that line, oops, we're going to have an intersection there. And it will look something like this. Oops. Sorry, that is not the best curve. So let me move over here and just draw the inverse tangent function. We're going to have something like this, okay, where we have a horizontal asymptote at negative pi over 2 and pi over 2. Okay, so this is what our curve of x equals the tangent of y looks like. Well, then according to our region, we also have the line x equals 1. So that's going to be a vertical line here. We also have y equals 0, which is the same thing as the x-axis. So the region that's bounded by these things is this little almost triangular region here. And we're taking that and rotating it around the y-axis. So notice that we do have a gap here. Okay, so because there's a gap, we are going to have to use the washer method instead of the disk method. So to help us find our radii, I'm going to go ahead and erase that gap notation that I had, because we need to find the inner radius and the outer radius. Now the inner radius, we're going to start with our pencil, whatever, at the axis of revolution, and then we're going to draw a line perpendicular to that until we get to our region, okay? So this little line segment here is our inner radius. Now we're rotating around the y-axis, so this inner radius should be something in terms of y. Our outer radius, we're going to do a similar process. We're going to start at the axis of revolution, but now we're going to draw it all the way through our region. So start and then end there. So that is going to be our big radius. We also should label our intersection points. So we have a point at the origin, 0, 0. We have a point when x is 1 and y is 0. And then our third intersection point, clearly that's when x is equal to 1. But if x is equal to 1, then y is equal to the inverse tangent of 1. So this is asking the question, what angle gives you a tangent value of 1? Well, that is pi over 4. So that means that this point is 1 pi over 4. Okay, so we have a sketch of the region, and now we are going to move on to step 2. With the disk method, step 2 was just to find a formula for the radius. In this case, we need to find formulas for big R and little r, so the inner and outer radius. For big R of y and little r of y. Okay, so big R of y, we already labeled on our sketch. It's here. If we write it out in words, this is going to be the distance from the axis of revolution, which is the y-axis, to this outer boundary for our region, which is the line x equals 1. Well, the y-axis corresponds to x being equal to 0. So we want the distance from x equals 0 to x equals 1. We're talking about a horizontal distance, so we're going to do right minus left. So we're going to have 1 minus 0, or just 1. So our outer radius in this case is the constant function 1. The inner radius, little r of y, is going to be the distance, again, from our axis of revolution, so that's the y-axis. But now we are going to our first boundary. Well, that boundary is the curve x equals tangent of y. Again, the y-axis corresponds to x equals 0, and we're finding a horizontal distance, so we need right minus left. So that's going to be tangent of y minus 0, or just the tangent of y. Our third step is to find the bounds of integration. Just as with the disk method, the bounds of integration are the smallest and largest values in your shaded region. So in this case, we're integrating with respect to y. So that means we need the smallest y value and the largest y value. The smallest y value is very clearly 0. The largest y value is pi over 4. So then our bounds of integration are going to be from y equals 0 to y equals pi over 4. And our fourth and final step is to integrate to find the volume. So the volume will be equal to the integral from c to d of pi. Then we'll have big R squared minus little r squared. And we're going to be integrating with respect to y. So we can pull the pi out if we'd like. We're going to integrate from 0 to pi over 4. Big R is just a constant 1. Little r is the tangent of y. And then we'll have dy. So now it's just a matter of how do we integrate this. So we have pi integral from 0 to pi over 4 of 1 minus tangent squared y dy. Now what we have ended up with is a trig integral. So you should think about what kind of trig identities can be used here. We have an identity involving tangent squared. Specifically, tangent squared is equal to secant squared y minus 1. This is from our Pythagorean identity, which is normally written as tangent squared y plus 1. equals secant squared y. So we'll rearrange that and substitute in, so that we get pi times the integral from 0 to pi over 4 of 1 minus secant squared y minus 1 dy. So this is equal to pi integral from 0 to pi over 4 of 2 minus secant squared y dy. Now the reason why we've done this is we can integrate a secant squared immediately because it's an antiderivative. We cannot immediately integrate tangent squared. So we've rewritten it in terms of something that we can integrate. So we're going to have 2. If we integrate, pi, if we integrate 2 dy, we're going to get a 2y. Then minus the integral of secant squared is going to be tangent y. All this gets evaluated at 0 and pi over 4. So we get pi times 2 times pi over 4, or that would be pi over 2. Then we'll have the tangent of pi over 4. Then we'll have minus 2 times 0 minus the tangent of 0. Thankfully, the tangent of 0 is 0, so all of that goes to 0. And we are left with pi times pi over 2 minus the tangent of pi over 4 is 1. So we get pi squared over 2 minus pi. And just for good measure, let's go ahead and add our square units. So our volume is pi squared over 2 minus pi square units.